Hi, I'm Alan, and today I'm going to talk to you about the Federated Project process. To introduce myself, my name is Alan Walker, and I'm the team leader for design and drafting in roads and highways for the SMEC team. I've been in the industry as a civil designer for over 20 years and had experience in the development and presentation of a number of civil projects from initial concept through to detailed design and construction. As a team lead, I'm responsible for managing my team's work allocation, project delivery, plus providing leadership throughout their career development. I'm passionate about the digital transformation of the business with involvement in SMEC's Innovation Committee and lend assistance in the development of digital engineering solutions to SMEC's leadership team by way of 12D and 12D Synergy. In today's presentation, I'd like to talk to you about the challenge, an overview of the solution with a breakdown of some key tasks, the outcome, a project example, the outlook with a discussion on what's next, and a final summary. So the challenge. Large-scale projects typically have multiple designers with various disciplines and require them to be interconnected with each other and deliver a consistent output. We wanted these interconnected disciplines to have live information to reference each other. Each discipline on the project had a different skill set, a different background, and a different set of models and tins to produce their individual discipline. What we wanted was for them to manage a consistent naming convention across the project. To maximize efficiency, we wanted to produce a solution that didn't require them to down tools for half a day or more in order to capture the latest content. To minimize double handling of models, we wanted the drainage team, who generally run behind the road designers, to base their design from a regular updated static version whilst the development was firming up. And finally, we wanted to risk the time it takes to do regular deliveries by maintaining the quality of product. So our solution was producing a federated project workflow. By creating a federated project process with this workflow, it allowed the design team to continue the project's development and capture a snapshot of the designer on a regular basis for formal client delivery. And this was done without interrupting the design team. So what was involved? At a high level, this is what takes place. The design team would check in all their projects via 12D and Synergy at the agreed time and date. Once checked in, the 12D model manager would open up the federated project. The federated project is a separate project, essentially an empty project. It required models and tins from all disciplines and work packages to be shared in. This data was then duplicated into the project as a snapshot at the chosen frequency of the project's requirements, in most cases weekly. Attach any attributed data that was not natively created from a snippet or the pavement manager. Create any additional tri-mesh objects needed, such as minor street furniture and line marking and signs. We would verify the quality of the data from the design perspective to the model quality with an approval process to roll back if required. And finally, we would batch output everything as a time-stamped regular delivery for handover to a project model manager for third-party model federation. And this was done via a work-in-progress shared folder setup. In the next 4 slides, I will take you more granular in the 4 key components. The first and foremost, and one of the key successes to this process, was the use of master share files. Master share files were used to ensure correct modeling was to be shared. Upon opening up the federated process, all data would be synchronized to the latest version. By creating a federated model master share, this fed back to the drainage and utility teams in order to minimize the disruption of constant changes, particularly at the beginning of the project. It enabled the internal work packages to share with each other for design tie-in, and it minimized conjecture for subscribers to those files. The next point for this to work effectively was to have consistent naming convention across the entire project. This stemmed from strings, tins, models, all the way through to functions, chains, and outputs. This was important for a few reasons. It took the guesswork out of the design team for their individual projects to populate the data. It meant that onboarding any new designers to the project was done quickly and effectively, or for them to pick up where another designer was left on if staff changing was required. It allowed the setting up of discipline chains within the federated project to have the use of stars and question marks, and this helped minimize the rogue naming of models and identifying obvious missing data. This was achieved by constant communication across the project with the use of a 12D user manual for the project, which was accessible by Synergy or the custom user menu. Having a working spreadsheet with examples of these naming conventions. The use of standard snippets that were used across the project. Manipulating the apply many defaults, and using standard layout files. With the new data all shared in thanks to master shares and a consistent naming convention, the next step was to duplicate this data. This was handled with the use of one master chain file, and this chain was made up of sub-chains that were broken into each specific discipline. Discipline examples of these were drainage, roadworks, railworks, utilities, and road furniture. Some of these were then further broken down into models and tins, as each chain had similar yet different sets of commands. The individual functions of these discipline chains are dependent on the project requirements. Typically, they included the following commands: clean previous version, duplicate and consolidate data to a checked version, apply specific attributes using the attribute manipulator file by way of project and synergy data or custom attributes, visual modifications such as deleting construction strings, and for the tin chains, additional commands were included, such as recalculating or creation of tins, nulling strings, and generating contours. The master chain file controlled the federated process with hold points where manual checking was required. Of course, nothing was submitted to our clients without a quality check, and therefore the next was to verify this data. This came in two streams, from internal model review carried out by the 12D model manager and a generic design check carried out by a reviewing engineer or design lead. For the model review, visual checks across the model were done, and this included comparing the shared data versus the duplicated data. Reviewing the output window to ensure all chain files ran correctly. Check the discipline models in the string information table for null strings, and this was particularly handy for quality D utility information. Writing out CSV files to check attribution and duplicates, and then read back in if correctly. And there was also a use of running the attribute validator tool if required. For the geometrical design review, a separate 12D design project was labeled verification was set up, which the design lead or reviewing engineer could access outside this project stream. The newly duplicated models with the label check were shared into this project via the federated model master share file. This verification is totally independent and required sign-off before commencing to outputting. Once this data was verified, the final stage is to convert the name of the consolidated model data from CHK check to final FNL. And this was run the final chain outputs. The purpose of exporting this data to a separate federated model the purpose of exporting the data is to separate out the federated model information into individual file formats and disciplines as specified by the project's digital engineering execution plan. These formats are commonly exported out as IFC, 12DA, 3D DWG or DWG, and other various file formats. We found two methods to exporting out this data which were required for the third-party model federation. Exporting files out to an output folder or an external folder, or exporting them out to a third-party CDE such as Synergy or BIM 360. Each option had its pros and cons and was dependent on the project-specific requirements. Option 1 for an output folder allowed export files to be collated into one location and then moved by the model manager to transfer to the model manager for federation. This export ran quickly and smoothly and providing a clear output from the previous file. The export of each file in the chain would run with a prefix text attached to it, such as output, sending it to that location. Option 2 allowed exports to be directly exported to a specific folder location, which minimized the double handling. However, the disadvantage is the prompt came up with a replace file, which became quite challenging when the chain file became quite large. Through this workflow, we can compile a federated model that requires the client's needs. The efficiency gains have significant impact on the projects, delivering a better value for our clients, correlated to the engineering information requirements. The total federation process takes approximately 2 hours from the beginning of the project and upwards of half a day in each as the project progressed. It became heavy on the detail and timely as the project went on. Although this process was upwards of half a day, to do this process manually step by step would entail at least half a day or more, or over half a day or more, and this efficiency of automation saved hours when tallied up at the end of a project. This process can also be handled by a third-party 12D operator, which is completely detached from the design team. In our project's example, which has been quite successful in the process, was the North East Link project tender services. This project ran regular federations. It was spread between 5 major portions and had 2 sections solely dedicated to 12D. It required 2 concurrent federated processes, each owing up to 4 minor road sections and other multi-disciplines internally. The federated process ran weekly and took approximately 2 to 3 hours to compile, upwards of 10 gigabytes of data. By using this weekly federated process in these 2 sections, it saved approximately 8 hours per section per week just on federation, resulting in upwards of 200 hours per project for the duration. The federated project process using 12D and 12D Synergy was something our team at SMEC have been working on and perfecting over the last couple of years. As such, we are constantly reviewing and improving it. Some of the challenges we experience are mesh files tend to be quite heavy on the detail, and so consequently the master share files for each project were duplicated with a no mesh version to be shared amongst the interdisciplines that didn't require them. Without removing the meshes from the master shares, there was a constant refreshing and syncing of the latest information to get this information in preparation for the process. The federated projects could take upwards of over an hour to open. IFC of files were as large as 2 gigabytes plus in the later stages of the project, which became challenging when double handling if required. The federated 12D project size became very large and relied heavily on one person exporting the data. Future projects, we would consider multiple federated projects to allow more than one person to export and potentially limit the project size, as we mentioned on the example project. As mentioned in the previous slide, we're forever evolving this process. We will continue to automate the chain files using parameters and integrating into macros. Further development of this process is continuously evolving and sharing across the business and beyond in forums such as this. And we would also look in further standardizing this process to be compliant with the ISO 19650. Thanks to the combination of 12D and 12D synergy, it enabled the integrated solution that created time efficiency, resulting in a cost saving. Additionally, assisting in the education and training of less exposed 12D staff with the tools necessary to complete full-scale digital engineering projects. Overall, this process has been a catalyst for the success of many projects. It automated the creation of project information models and the asset information models for 3D outputs, enabling the PIM and AIM to be fully compliant to our DXPs. It created efficiencies in 2D outputs for drawing production, resulting in time and cost saving. And ultimately, it de-risked project deliveries. Thank you for your time.